Now that we've dealt with the parabola going, or rather the graph of the displacement versus time, we've got to look at graphs of motion, okay? These are much beloved problems by examiners. So let's have a look. What are we talking about? Do you remember back in earlier classes where we did graphs, okay? We did ticker timers, if you remember. Remember the ticker timer was a piece of paper and it's attached to what they called a trolley, and you put a force on it and you measured the distance between dots and you calculated various bits and pieces from that. It's a very, very cool experiment to do. It's quite fun. And the nice thing is it usually works pretty well. Okay. So what did we get? We got if you remember, I'm going to put my ticker tape timer A, B, C, D, and say E over there. All right. Let me just label it as A, B, C, D, E, and F up there like that, right? Now, what did we do? We went along and we measured all of those distances, right? So we calculated in meters like so, those distances there like that, okay? Now, the next thing is that was all on a piece of paper, right? I haven't drawn the piece of paper in, okay? It's pretend it's like that, right? And it just goes. Now, the thing that made the dots was the ticker timer, wasn't it? And each time it hit the piece of paper, that we measured was the frequency. Now, usually they give you the frequency. They will tell you the frequency is going to be 50 hertz. And remember, the time is 1 over frequency. So the time between dots is 1 over 50, which I should know off by heart now, but I don't. 1 divided by 50, I think 0.02, mode 1. 1 divided by 50 is going to be equal to 0.02. So time is 0.02 seconds between consecutive dots, which means da, 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 da. 0.02, 0.02, 0.02 between. Usually in these types of problems, the ticker tape timer they give you that's labeled, that A, B, C, D, E, that could be every 5, 10, or 20 dots. The example I've done here, I have said it's every 10 dots. So in other words, between there and there is actually 10 dots. I have highlighted only every 10th. Therefore, the time between those two is going to be equal to 10 times 0.02, which is 0.2 seconds. And t equals 0.02, t equals 0.02, t equals 0.02, and t equals 0.02 seconds. The time between each of those A, B to C, C to D, etc. is 0.2 seconds. And Kevin wrote 0.02 because he was thinking of something completely different. What a silly character. My apologies, guys. It's 0.2. Oh, come on. It's 0.2 between. 0.2. See how easy it is to make a mistake, eh? So it's 0.2 seconds between each. All right? So how do we do these problems? Remember, what did we do? We dropped a line down there. We dropped a line down from each of the points. Okay? And then that is... Now, we know the distance and the time, and distance over time is velocity. So therefore, I can say what is the velocity at B is equal to delta x over delta t. Remember, the velocity is thus that distance there divided by 0.04. Because it's why am I doing that? It's 0.4, Kevin. 0.4. Because this is 0.2 and that is 0.2. All right? This is very mechanical process of doing these things, okay? Then the next is to say, okay, That gives me the velocity there. I find the velocity. So I've got the displacement. Find the velocity at C. Velocity at C would be take the displacement. I'll just do it in blue. You take that distance divided by 0.4. Okay. This distance here, whatever it is, divided by 0.4. Correct? That essentially is our displacement over the time, right? Then, if they want the acceleration, what do? The acceleration, I'll just move it to green. Let's just take it up a little bit. On the acceleration, I say, okie dokie then. I then take velocity at C. Just make that a nice V. Velocity at C. I've already got velocity at B. So my acceleration is going to be velocity at C minus velocity at B divided by 0.2, because that's my time between those two velocities. Right? They could have given me velocity. I've asked for velocity at B and then velocity at E. I would have done the same thing, except I'd have gone between D and F, correct? I'd have taken the total displacement. Well, let me just do it in green. I would have taken that, and I would have taken this number and divided it by 0.4. That would have given me velocity at E. Then I would have said the acceleration is velocity at E minus the velocity at B over here, right? And divided by, and I know I've said 0.2, 0.2, 0.2. It would have been 0.6 seconds, correct? That's how I would have done the standard ticker timer problem. Now, let's just have a look and say to ourselves, all right, let's go back to our graph of motion previously, shall I? Remember the one we just did with the ball going up, etc., etc.? It was a certain distance up. So essentially we had a problem where we had an object like that, and this object was thrown up and it went down like that. Okay. Now let's draw the graphs of motion of this thing. Okay. I'm going to just draw it like so, and like so. Okay. This is going to be my positive delta x. This is my minus delta x. Okay. Because delta x could be negative depending on where I start, right? That's the important thing here, guys. If you start at a different place, you could have a negative displacement, all right? In other words, it's moving away. We're going to get to those now. This is going to be this. So this is my delta x versus time. Time on all of these axes over here, all right? Now, what do we do? Well, let's say, what do? We say at time naught, where am I? Well, at time naught, I am plus 20, aren't I? So therefore, I am, in my old example, I am there. Then we said my graph did this, remember? Okay, like so. Therefore, what do I know? Well, we know that at that point there, it was 2.04, 4.08. Doing that, isn't it? Right? All I'm doing is I'm asking, where am I at what time? And I can plot my displacement, because my displacement up here, this was 20, and I think, if I remember correctly, let me just go back and check, my height was 20.4, so that's going to be over there, that's going to be 40.4, and that does that, correct. Now, let's have a look at the velocity. Right? At time, this is plus v, this is minus v. Okay, yep, the bottom one's going to be acceleration. At time 0, what's my velocity? My velocity is plus 20 meters per second, because it's going up, isn't it? At this time here, what's my velocity? 0, because I'm at the turning point. So my velocity is 0. So what happened? It did this, correct? Okay. Then what happened after that? My velocity carried on increasing as it went down, and at this point over here, it reached its Vmax, whatever that was there. Right? Let's think about it. It went, the velocity initially was when I threw it, and as it went up, remember I threw it from a height here, went up, 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 stopped, and then accelerated, and down, 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 down it came. Right? My velocity down here, we haven't calculated it, but you could. All right, because you could work out how high it went. Then you know that there's 40.4 meters up here. So I could technically go and say, right, if that's 40.4, okay, what would my velocity be at that point? All right. So all I've done is I've said my velocity started at plus 20 there. It's 0 at that point. So all we're doing is we're filling in the bits of information that we're given. That's it. The last curve is the acceleration curve. Now, the acceleration curve, what did we say? As you go up, acceleration was minus. So yeah, there we go, until we get to the same point. There's minus acceleration plus acceleration. And on the way down, until I get to that point, this is plus 9.8 minus 9.8. Right? So this is my acceleration curve, is two straight lines like that. Right? The key points of this is to say, where am I at what specific time, or what am I doing at any specific time? Okay? That is the key. Let's look at a different problem. Well, not a problem. I want to recap here. Let's have a displacement time graph. Hang on, let me just give myself a wee bit more space here. Otherwise, I'm going to run out. Okay. Okay. This is a displacement time graph, and I'm just going to try and fit it all in. Okay. Going like that, then a straight. No, it's not going to fit in nicely. I can just take it. Nah, I've got to rub it out. Always happens when you try and draw what's on a piece of paper, when you try and draw it onto a thing like this, isn't it? Okay, I'm going to have to use it, slide it down. All right, so I've got now initially a curve doing this. Then I've got to there. Okay. Then I'm going to change that to a red straight line to there. Then I'm going to put in a green, green one, which was this guy here. All right. I'm going to continue green like that, which is like so. Then I'm going to put in a blue line coming down here, straight line like that. Okay. So I've got now three curves. The first curve over here is a parabola. Okay. What is happening over here from A to B, right? Well, let's just think about it, right? This is my plus delta x. This is my, I'm not going to do a negative displacement at this point. All right, that's my plus. I'm only looking at that first parabola curve that does this, right? What is it doing? The body or the object is accelerating in a positive direction, right? Which means it is going away from me faster all the time, if you think of it like that, okay? So the first part is a parabola, is an acceleration away from me. Then we say, what's the second part? The second part is a straight line, okay? So the straight line means it is now traveling at constant velocity. Remember this from last year's or the years before? Then the upper part of the parabola, C to D, to E, and to F, like so, right? That's because it can't keep seeing me. So what have I got here? I'm saying that between B and C, so A to B, let's just put and make a note here. A to B is a acceleration away from me, because I stand at the origin, right? That's what I do. So it's accelerating away from me. Don't worry, we're going to do examples of these. I've got quite a few of them that we're going to do. It's accelerating away from me, right? Okay, then the next one is B to C. What's it doing between B and C? B and C is constant velocity. Okay. And C to D, it's got a negative acceleration. Okay. In other words, it's going or accelerating but still moving away from me. It's got a negative acceleration. If you like, it is stopping. Okay. It is coming to a standstill. The next part is it's then accelerating back towards me. Okay. D to E is acceleration toward me. All right. And the next one is the straight line is A. E to F is constant velocity towards me. How do I know this? Look at the displacement. Where is it? After, let's just put in some numbers. These are totally hypothetical numbers, guys. Okay? Let's say that's 10, that's 20, and that's 30. Over here again, okay? So after so many seconds, this is time here, right? After so many seconds, it's at B. It's 10 meters away. Then after another time, it's 20, then 30. But now look, over here it's 25. Over here it's 15 away. Which means, what did this vehicle of ours do, or this object? It went away from me, okay? Then its displacement, it must have come back to me. Please just use them, become the vehicle or the car or the object. Ask yourself what is happening. I am getting further away and then I'm getting closer, which means I must be coming back towards me, right? You have to approach these graphs from a logical point of view. There isn't just a straightforward sit down and maths with this, all right? It just goes higgledy-piggledy and haywire if you try it. The only way is to sit down and say, where is this object from a displacement graph? Then it will become painfully obvious what's happening, all right? The next phase is to say, okay then, let's look at a velocity time graph, shall we? Velocity, which is plus V, minus V, and time. Remember again, what did we do? These are our key points, all right? All we're doing is putting in the key points. At this point here, I was told, let's say it starts from rest, then it goes up to that point. Here it's at constant velocity. Here it is now stopping, okay? It has now stopped at that point because the displacement is the same. It's continued this way and then a constant velocity over that last piece there, right? Right. And now let's look at the acceleration section of the graph. All right. What happens with that character now? Okay. All right. This is plus A, minus A, and time again. Well, initially there was an acceleration away. Then between here and here at constant velocity, no acceleration. Then between there and there and there, there's a deceleration, correct? Like that. Then there's 0 again on the last bit, right? Well, why? Okay, let's have a look. Remember back, just to refresh the memory. Okay, notes. Let's just go through this carefully now. Okay, on a displacement versus time graph, delta x versus t. Remember, when you're given a graph, right, look, step one, look at axes. Is it delta x versus t? Is it v versus t? Or is it a versus t? That tells you the type of graph, and we're going to use these from there. So we say, okay, in this case, it's a delta x versus t. Note 1. Okay, the graph, the slope of it is your velocity. Okay, so this is constant, this is plus, that's minus, right? So what we're saying is the slope, remember, slope is delta x over delta t, which is equal, let's say m is that, which is our velocity, right? So if you look at the slope, the straight line, all right, up, all right, you have a increase in velocity, okay? You have a positive velocity. Now, if you look at the slope of a parabola, remember, those of you who've done calculus, it's a changing slope. That indicates acceleration if you're using calculus to solve this, right? But we're not at this point in time, okay? So, let me just move it up slightly, okay? The other thing about it is on a VT graph, velocity time graph, all right? The slope, okay? The slope is delta V over delta T, which equals acceleration, right? So you look at the slope, right? Velocity over there is the slope. Acceleration plus or minus, right? And also on this one is number 2, is the area is the displacement, all right? The area under the graph is the displacement, okay? Right. Now, just for this last piece of this one, I'm just going to talk. So how's the best way to approach these? First of all, you check the axes to see which graph we've got. Okay, now you have to learn those other bits and pieces or get the concept of looking at the slope of the line, all right? Obviously, if the slope is like that, on it's a delta x versus t, look what Kevin wrote here. Okay, delta x versus t. Okay, displacement versus time. Sorry, guys. If it's like that, okay, what does it mean is the velocity initial and the velocity final are the same. Because when we go through these, okay, I'm just going to go back up to my graph over here. All right, let me go and get blue. Remember, this is VI, this is VF. This is now VI, VF. VI, VF. Remember, this is what you do. You split them into individual sections, right? Sorry, it keeps doing that because of my eye contact. It's a new thing. What we're doing with it is we're saying, right, you can see there that I've split it into each individual section. That's the way to do it. So you take the first time section, and if it's a velocity time graph, look at my velocity at the beginning, the velocity at the end. That will tell you and allow you to work out whatever else is needed. All right? Let me just check, make sure. Identify the key points. Usually it's a velocity or a displacement or an acceleration for a particular time interval. Hey guys, it's here. This is our time. So if you know those times, you can say to yourself, what am I doing or where am I at that particular time? Between each one of these, A to B, B to C, C to D, all of Newton's laws of motion apply. Okay? Then ask the question, what is happening to me at that point? What am I doing at that point? In other words, the object. What is the object doing at that point? Okay? Is it stationary? Is it a V? Let's have a look at this point here. Okay? Just for argument's sake. Here we go. Let's look here and here. Velocity initial is whatever. It doesn't matter. Say it was 10. And final is 10. Which means the velocity didn't change over that point. Okay? These you have to use logic and deduction powers. No, you can't just bang it into a formula. Like much of physics we can, I agree. With these you can't. You have to ask yourself those questions, right? I'm going to do a couple of problems when we get back. I'm going to do bouncing balls and I'm going to do a few, I've got quite a few problems here that we're going to do. Okay? And these are pretty cool. Okay, so we'll do the problems and come back and let's go through some problems. This is not the easiest section of the work. Okay, so if it's getting a bit confusing or whatever, go back over what I've done now. Go back to the previous videos on this kind of work in the previous 2 years. Okay, Make sure you get this. I know a lot of students are like, whoa, this is coming out the blue again. It comes from 2 years ago. Cheers. I'll see you just now. Bye.